Okay, great. Okay, so I will talk to this then. Good afternoon. My name is Pierre Du Bois. I am the founder of Zamana Analytics, and welcome to Code PaLOusa. And I appreciate everyone coming out today. What we're going to do is we're going to talk a little bit about TensorFlow. You probably have heard of TensorFlow over the last few years in particular. It's been around for a little while. But so I wanted to do with this presentation was a lot of the things with TensorFlow is focused on Python because it was built around Python originally. But over the last few years, there's been a lot of development, particularly around R and R programming. So I thought I would get this as a primer. This is a talk I've given a couple of times before. This is my first time speaking about it since the upgrade to 2.0. I'm going to talk a little bit about that as well in a bit. So just to kind of give a quick overview, I'll try to keep switching back and forth here to make sure you can see the presentation. But the idea is that we'll try to give an overview of just, basically what is a tensor and what is TensorFlow. And we're going to talk a little bit about a framework for using it within R in terms of planning your data, planning your TensorFlow model, and then we'll have a demo in here. The one challenge is that this is a PDF that I had to load within the browser, so it may not play the demo here. So we may have to have that, but it will be built into the slides as a movie, so you can play that back at least. But I'll walk you through the steps so that way you have an idea of what to plan for or think about when you're thinking about your machine learning model. So let's get into it then. So the sort of this is TensorFlow is just was basically created through Google. It's a play on tensors and it's a play on the word flow, basically. Tensors have been around for a while, and what they are is basically a multi-dimensional array. It's a multi-dimensional array of numbers. Think of it as a number of nodes that are tied together. Each node is called an epoch. And in each node, you're applying some sort of mathematical representation of variables. And the general purpose behind this is to help take data and iterate a number of times to get to a particular, to identify an image, to identify a particular regression or some sort of equation. So in regressions, you can think of it as a type of taking different columns of data or variables of data and seeing if there's some sort of relationship and establishing a relationship. With TensorFlow, you are taking that premise and iterating it over different, actually iterating it over different regressions. So it's a little bit intense from a mathematical standpoint. But in real life, tensor arrays are supposed to reflect observations of products, services, or events, or items, basically. And so the idea is that each time that you are taking data, you are taking it and applying some sort of statistical application to help you figure out how things are identified, how they're clustered together, or how some sort of relationship should be established. One of the best ways of imagining how TensorFlow should look, I use automobiles quite a bit. My background, real quick, I was an engineer for Ford Motor Company for 8 years. Actually, in fact, I'm a little familiar with Louisville. I know Louisville built the Ford Explorer for a while, and I believe now they're building the Escape and the new Corsair. But the Explorer actually makes a really good example here. In automobiles, for example, you have certain trim levels that vehicles are sold at. And Ford discovered something very interesting about their Explorer. They actually figured out that people were buying a certain trim level called the Explorer Sport with certain features on the vehicle. And they got a little wise and said, why don't we just package those features together and make another trim level? And that trim level is known today as the Explorer Platinum. That's sold pretty well from the previous generation into the next. So you might be thinking, well, what does this have to do with machine learning? Well, in order to make a selection or a thought, you have to think about, in this case for Ford, they had to think about not just what features, but maybe what features should be packaged together. And if so, from a statistical standpoint, how sustainable or how frequent those features are being selected. In other words, if you are purchasing, let's say, a Ford Explorer Sport, and you want to have the latest safety package, and you want to have a power moonroof, and maybe say the something with high intensity headlights. Um, you know, some options, some customers may purchase the first two items maybe once or twice, but there may be but you need something that helps you to figure out, are they packaging all three of those together, and if they're purchasing those things frequently enough to be sustainable enough to say, hey, we need to put this into an actual model. And this is where TensorFlow comes into play. It's basically, you're taking data to help you predict if people are going to make this sort of type of choice over and over again enough to be sustainable, to say that there's a relationship. Same thing, we look at image recognition. For image recognition, and we have an example from TensorFlow 1 just to show, it's the idea that you are taking data and trying to figure out, based on certain pixels, based on whether there's a color to it, whether there's a 1 or 2 to it, or a number assigned to it, does it come together to form a number? Does it come together to form an image? And so that's the logic behind it. And this is where TensorFlow comes into play. So the way that an array works is basically, it's basically by dimensions. And so you have each dimension in an array has a different, it represents a different part of that array. So think of it as, the way to imagine is, think of it as taking their different pieces of what it is that you want to model each time that there's a set of data. So for example, there's a 0D for a scalar. There is a 1D, which you use for scale and direction. And then there's a 2D, which you use for vector data. That might be what's called samples and features. And samples is just sort of the best way to describe it is more like a simple a characteristic that's held. It's kind of more of a mathematical thing than anything else. But think of it as just as kind of a row of information, meta information that's associated with data. So the idea of thinking about this would be, from our car example, we might have, let's say we have maybe a sample, and then maybe say another set of data that might be observations for whether or not if a vehicle is ordered with a moonroof. Okay, so that would be maybe a vector data. Time series data could be thought about in terms of, would add another dimension. So you have samples again, and then you would have maybe a feature, and then maybe some point of time. So that could be something in terms of, again, ordering some sort of product, but maybe on certain days or certain period when those orders come through, and so forth. So each dimension is supposed to represent some sort of feature with some sort of sample built in. Okay. So in a TensorFlow network, this is sort of a kind of hard to I had to kind of come up with a way of kind of showing you how this would work. But in a TensorFlow network, what you're trying to end up with is a set of layers for each one of these epochs. So you have what's called an inner layer, which is the data that's being input in. And then you have hidden layers, which are meant for transformation. And these are the layers that are taking that data from the inner layer, and then having some sort of implying the mathematical relationship. And this is something that there's different models that that are already built into TensorFlow, and there are models that you can build out of using R or Python. Basically, we'll get to that in a moment. And then your output layer is a predicted layer. So the idea to think about this is, again, using automobiles, is this idea that you may have data representing certain features. Maybe, again, a timestamp on when somebody is ordering a Ford Explorer. Another set of data showing that maybe a 1 if the person purchases it with a moonroof, maybe a 0 if they don't, and then maybe, again, maybe 1 if someone purchases with a safety feature, a 0 if they don't, and so forth. And then the idea is that once that data is placed, this is where R, Python, and a lot of the languages come into play. Once that data is placed into a program, with TensorFlow, you are applying a mathematical model to help figure out, what's the likelihood that one feature is ordered with another feature. And then your output layers are predicted prediction that basically states that that the likelihood that this model holds up very well, basically. So your output layer is basically and we'll see this later on a little bit. It gets into more of the kind of a loss function, which is a little bit more machine learning. But the idea is that you are trying to kind of, with this model, you're trying to see how well it not only predicts the certain relationships that will happen, but also how well that holds up. That's the idea. So your data can be of what, going into categories here. It can be a continuous data, like, for example, price, continuous observations. It can be something binary as a yes or a no, or it could be a category identified as an image or sound. And this gets into image recognition, the idea that a pixel is taken and you're trying to categorize if something is there or not, basically. So what are the applications for TensorFlow? Well, there's quite a few of them. Again, I hint a little bit at time series prediction as being one of them, but TensorFlow can be used for a number of things, that anything that you're thinking about in terms of machine learning, in terms of some sort of prediction. And if you have a lot of features and you're trying to figure out not only what features go together, but maybe which ones should be held. There's a couple of functions that get into that. We'll talk about that later on in the presentation. You can use it for customer churn prediction. What are the factors that go into whether you churn a customer or not? Image recognition, I mentioned before, is a very popular use, and you'll see there's a lot of examples that are on the TensorFlow site. Voice recognition is also coming into play. The idea that you can take a voice and put it into a file means that now you can use some sort of voice recognition. So it's basically a lot of prediction of complex, you can do a lot of prediction of complex spatial or sequence dependencies. So for example, something along the lines of trying to figure out if certain features have a, kind of going back to time series a little bit, the idea of certain features are, they're grouped or categorized based off of something within time, or there's some sort of distance that tends to cluster or group things together. That can be used. That's where TensorFlow can come into play. Okay, I keep my eye on the time here a little bit. So why TensorFlow and R programming? Well, it's a lot. I mentioned a little bit before. Most of the TensorFlow has been developed around Python. That's why if you go back and look at any sort of video, any sort of help desk, or any sort of help information, you'd see probably more Python than anything else. But in the last few years, there's been a big breakout of other frameworks around TensorFlow. R programming is one of them. You'll see quite a bit with JavaScript, where you can take actually a JavaScript script or call up through npm through the Node package manager and basically run data through JavaScript. The purpose of that came into play because it allows you to run data not only at the browser, but for other devices that may be that are using data, may have it in the form of JSON or some sort of format to make it, or some sort of JavaScript related format. So there's a JavaScript framework that's available for TensorFlow. Swift is the most recent. This was introduced, I believe, just the last year. I think it was just with 2.0 it was announced. So this is very, very recent. There's probably, I know there's a few videos on it, but probably not a whole lot in terms of help, in terms of a background. But the point of this, and there is a TensorFlow, by the way, for quantum, there's a TensorFlow Quantum as well that was introduced. And this is for quantum engineering, quantum analysis, so, or quantum programming. So basically in the last few years, there's just been this number of different applications for it And it's just basically allowing people to take a machine learning framework but use it within the language that they feel comfortable with. And for R, there's a lot of data science people who, some people it's getting less so now, but there's quite a few people who debate about whether R is better than Python or whether Python is better than R. I'm not one of those people, to be honest with you. But one of the benefits of it is that a lot of R is designed to take data, place it into columns, and read into a column and help in terms of planning a statistical model. And most of the people that you find that have used R programming are a little bit more familiar with the data than they are with the programming part. So you'll see a lot of people who are doing R statistics for COVID, with a lot of things going on with the pandemic. You see a lot of people doing R who are in healthcare and maybe more familiar with the data itself, and maybe are interested in making some sort of trying to establish some sort of relationship between different variables of that data. So so R tends to attract programmers who have some sort of familiarity with the context or the subject behind the data. And that's kind of what the idea is here. So you get basically this blend of using TensorFlow and Keras functions with R libraries that you may be familiar with. So one of the things you want to keep in mind when you first start out, as of right now, there's a TensorFlow 2.0. And when we run through this, there's a slide on here that I'm hoping that it came out as a movie. If not, we may have to see if we can play at the end here in a bit. But the idea with it is that you want to be at version 3.6 at least as a minimum. Right now, I believe R is at 4 as a few days ago, as I've just checked. But even if you're running a few older versions of R, I would just say just check if you're at 3.62, because otherwise you'll probably, I believe that TensorFlow and I think Keras, I think they're both a little wonky. And one small point too, if you have a Mac, if you're running Python, if it's like a Python 2.7, you may want Mini Conda to help you recognize, and maybe want Python 3.6. That's just kind of a disclaimer here. I noticed when I was running this, I had a time trying to go back and get this to run correct. But the point is that you do want to be up at the latest R if you can be there. And then R libraries that typically come into play, Keras and TensorFlow are the libraries that you would pull. Is there anyone in here let me back up just for a quick second. Is there anyone in here who is not quite familiar with R programming in terms of libraries and packages? I'll take a quick second. I don't see. Okay. I don't see anyone typing. Me. Okay. So thank you, Tina. So so let me back up a little bit on what this is about. So in R, when you first R is usually run, you can run it through RStudio. There are you can run it as a standalone, but if you go online and look at any video on whether it's YouTube or through RStudio, which they have a bias because that's their IDE. Most people will run R as within a RStudio. And RStudio is an IDE. It's very popular among R practitioners. They just now started to, I believe you can run Python in it now. But the reason it's popular is that it gives you a couple of windows that you can operate in to see not only your data, but also to see your file, and then also to see your output. So it's very popular that way. There is from my understanding, there is a Visual Studio Code. There's a couple of extensions that will allow you to run R in Visual Studio Code. But I would say to make it a little easier, if you can do it through RStudio, just because there's just so many videos that are out there, most just come with by default. That's a great way of starting out. So when you do start, libraries they're basically extensions. No different than maybe say plugins that you would have for other languages. But what they're designed to do is R comes with a very basic statistics, can do very basic statistic calculations. When we do a faster workflow tomorrow, That's my session in the morning. We'll talk a little bit more about that. But one of the things what libraries are designed to do is allows you to not only do advanced calculations. You can actually create a library and save it in a package, but they also allow you to connect to outside servers, and they also usually bring in practice data as well. And so tying into TensorFlow, what you're doing in this case is that it is providing the layered framework for TensorFlow, and you'll hear Keras quite a bit too. It provides that framework to basically allow you to run it as well. And there's other frameworks associated with TensorFlow too. And we'll talk about a few of those here. One of them is TF dataset. That should be data sets on the slide actually. And TF datasets allows you to upload it's an additional library, but it allows you to upload a not only a practice data set, but it allows you to also upload connections for larger, allows you, if you have larger image frames, image data sets that you want to load up, it will allow you to do that within R much more easily. And that actually requires another dependency, Dipler, which is a very popular library as well. Where you would go to get these is cran.org. And these are free, by the way. All these are free. CRAN is a repository where you would go to search and look for libraries, and you can import those into your RStudio IDE, and then save everything as a project. So that way you have those libraries at the ready the next time you practice through. So in short, that's a real quick overview. So let's talk about the data for a second, because a couple of things that you want to keep in mind with data structures a little bit. Within R, like any other programming language, R basically will take data and you have to put it into a variable. So you're taking data and assigning it to a specific variable. But one of the challenges is that within R, the observations have to be sort of arranged in a certain way. This kind of gives a light example. So right here at the top, I have an example here. Let's just imagine that this is a very simple spreadsheet that was given to, let's say, a car dealer, and it's used cars. So they have the last generation Corvette, the C7, and they have an F-Series, and they happen to have two used vehicles, a Honda Passport, I know I'm dating myself on that one, and a Volkswagen Jetta. And this dealership has a certain scoring value that they have. So a Corvette gets a 1, an F-Series gets a 2, the Honda Passport gets a 3, and then the Jetta gets a 4. And that's what you see on the column on the right where it says numerical. So it's kind of like a numerical rating. And then sample might be the actual car itself. So the first car is a Corvette. Second car is a Corvette. Third car is F series. So you get this spreadsheet. And let's say you're a used car dealer. Your boss gives this to you, and it's a complete spreadsheet from your standpoint. But from our standpoint, there is a problem, and the problem is that the categories are all within the. If you look at things as a column, sample has numbers in it. Numerical has numbers in it. So sample would be more like a count, where numerical has like pretty much a rating system. So you kind of know there might be a range. But category, you have text. And R tends to prefer that you are taking that text and that there's not text in the observation. And for TensorFlow, you don't want that. What's going to happen is as TensorFlow operates, it actually goes down a column. So what you want to do is this is where data cleaning comes into play. And what you want to do is you want to at least transform your data into something that takes the categories out of the data fields, out of the data fields, and places them into some sort of header or column, basically. So what you're doing here is that this is basically relying on your knowledge of the data to figure out where things should be placed. So this bottom image, for example, is very similar to the first. It's just that now you have Corvette in one column. We have the 1's rating right there. It's the third vehicle is still an F series, and now you have a 2, and there's zeros in there, and the other observations. And in Passport, you have sample 4 and sample 6 having their rating and so forth. So the idea is that you now have these sort of numbers that basically are assigned within the observations. You basically have it set up in a way that you can run within R. If that makes any sense. Okay. Can you post the link here, please? Okay. All right. We will. Yeah, I can do that. Let's see here. Which link did you want for that? I'll let you type it up as we keep going along here. So the idea is let's scroll up here. So the next area is we're going to try to create our training and test data, and there's usually a there's usually a split between test and training data. Usually an 80-20 split is where it's kind of pretty much where people start basically. But there's a lot of different ways of importing data into TensorFlow. This section of code here, this is from an example from the TensorFlow site. They're taking a data set for Boston housing and assigning it into a variable, pretty much a container, a data table for Boston housing. And then on lines 12 and 13, if you notice right at the very end, you see Boston housing, which is that variable. Then you see a dollar sign, and then you see train, and then you see another one down. The second one says Boston housing dollar sign test. That dollar sign test is the name of a column. So if you remember what I was saying, you want to have columns. That's the name of a column that gets called out. And so a lot of this is being set up based on the number of columns that are in the data, and then basically setting up labels and the training data into kind of an array, basically. And that's what you're seeing here in this particular example. But there's a lot of different ways to do this. The one example I have for TensorFlow, and I'll show this on one of the next slides a little bit. It kind of does it a little bit differently. But in general, what you're looking for is you're taking data and making some sort of split, and it should be something that should help you identify it by column. And there's a lot of different ways you can do this. If you went into, even outside of R, if you use something like Data World, you can identify the split by column, basically. But usually there is a 80-20 split. There are libraries that lets you read data into R. Read R and read CSV are useful for maybe simple data. You may have specialized libraries like RMongo. That's for use for having R access data on a MongoDB database. And then there's a particular one for TensorFlow called TF datasets. And this is basically, you can use this for loading large image files or large data files, like very large, huge large files, where there's thousands of images, thousands of voice files, and this makes it a little bit easier. You can have those, again, called up as a variable or function within R. Okay. So once you have that in, so now the next thing you want to do is you want to be able to position the data as the columns of data as an input layer. And that's what you see here. This is an example that was taken from the first version of TensorFlow. And what we're doing here in this instance is that we're taking that data, we're basically putting a label and a column of data. In this case, that's what you're seeing from the steps from 6 to 10, and then steps from 15 to 16. And then in some cases, you may need to rescale data. Now, let me explain what I mean by this. This is basically normalizing data or having some sort of standardization. The reason that you do this is that you are trying to give depending on the type of data you're using, you're trying to give something that tells the machine learning to treat this particular observation as a 0 or a 1 or some variation of it. let me focus your attention on 21 and 22, line 21 and 22 to give you an example. This example focuses on, takes basically image data from MNIST, and it's placed into different columns. There's a X column for training, there's an X column for test. The lines 21 and 22 are taking, each observation is a pixel. And what it's doing is that it's taking those pixels and trying to apply a grayscale to it. And so by doing that, it turns, by taking it and dividing it by 255, which is a standard number, what it's doing is it's taking those observations and changing it into some sort of scale, into 0, 1. So the idea with this is that you are normalizing it into a range. That's the idea. That's the idea here. So that way, when it's run through each one of those epochs, you're basically, it's training to figure out how to classify an image as a 6. In this case, these are images, so the image of numbers. So it could be image of a 6, image of a 9, image of a 3, and then based on grayscale, it's trying to figure out. It'll be able to take that data and figure it out whether or not if it's a 1, 2, or 3, or so forth. Okay. Okay. All right. So then the next step is, of course, the core layers. And this is kind of where the programming comes into play. And there's a little bit more to this I wanted to go through, but it would take me much longer than an hour presentation. So I tried to think about what's the simplest way to explain this to you. So there's 2 parts to this. The first part is the model itself. So this model that you see, where you see model, Keras model sequential is applying a function into an object with an R, and then where you see layer dense and layer dropout, those 2 come together, combine to make a layer. Same thing, and then the next one would be dense dropout combined to make a layer, and so forth. You have what's called an activation layer, which is, oops, go back down, which is that first line at line 34, basically. And so the idea is that you are, you're think of it as putting your data through a strainer. It's taking that those observations and trying to classify into at one layer. Then you're taking it into the next layer and you're trying to classify or classify those observations in another layer. And then you have everything placed into a into the model. And what happens is you now have, then you'd have to do what's called a compile. Now let me explain what a compile does. Compile, the function of a compile is to help you go through what's called a loss function. There's a slide we're going to talk about this. If it sounds familiar to you, you probably heard the phrase accuracy and loss. These are calculations done in machine learning to help figure out if a model is overfit, underfit, or just right. And we have a couple of slides to talk about that in just a second. But what you do as a programmer is that you have the good news is that there's a couple of some of these parameters are come with the Keras and the TensorFlow libraries. And so like activation, you have ArrayLu and softmax. These are kind of standard parameters that you can start off with, basically. ArrayLu is usually used in the first layer, softmax at the end, and these are just starting points, basically. And then where it has dropout, the rate is an arbitrary number at the very beginning, but there is a function later on, I'm going to talk a little bit about that, where you can adjust the dropout as the model is functioning. And we'll talk about that in a bit. But the idea with this is to kind of give you a structure of your focus is on the data when you first put the model together. Then you use some of the basic pieces that are in TensorFlow. These are basic functions that are used. And then in the compile, which is created this right here, you would have a loss categorical cross entropy is a basic function that you would use. And have it set for that, just to run it through initially, just to get a very basic sense of the model. A lot of times when people are making adjustments to these models, they usually are using either some form of advanced math, or may have a particular research model that they've used. And I probably would say if you're just sort of practicing out, I would stick to some of the basics initially. Changes should not be just arbitrary. It should be just something that you are trying. It should be something that has a particular function or a purpose to it. And that comes only through experimentation. So that's, just keep that in mind. This is something just to give you sort of a framework to start with. Now, I mentioned about underfit and variance trade-off. So this is something you'll see with machine learning quite a bit. And I have regression in here. Loss function basically is the error between the actual and predicted values. So the idea is that you have a predictive value that's based off of the training data, and then you have another set of data, rather your test data, and then you have another set of data that you're training on, and then you may have another set of data just to kind of see if that function holds up well. So again, thinking about our Ford example, you've tested out with maybe some data and predicted which features you want to put in the package for your vehicle, and now you're trying to see, over time, if the next sales month, if that data holds together for your model, basically, if you can predict that people are actually going to buy that Ford with those features. That's kind of what the purpose of this is. So this ties into and it gets represented in the compile. So you have underfit, overfit, and then you have what's called a just right. So underfit is when the model is not really learning the trained data at all. I have regression here, so you can kind of see how that, just to have it in your head. Where a overfit, which is over on your right, is basically following too closely to the data set. So it's basically holding a tolerance that may be, when you talk about products, that may be, it might be, you may be spending more at something that you shouldn't have. If you're talking about anything that deals with social data, that can have a real cost in terms of maybe services or life, for example. A great example was, well, hold on my examples here, but real quick, there was one in New York where they used the machine learning model to figure out where to deploy their fire departments. And part of that was modeling the data of when fires had happened in the city versus where alarms where they had been inspected. And they used that to help figure out where within New York, with so many, with X amount of inspectors, that they should be sending people to better inspect and prevent fires. So in that instance, again, you might want to, if you overfit, that means that you may be in a cluster that maybe is too tight, or something that may overlook neighborhoods that really do need to have inspection. And then underfit will be something where you're sending inspectors someplace where you're not really hitting the actual neighborhoods the way that you should. So there's a real life. So I'd say this to say there's a real, depending on the type of data you have, there can be a real life and there's real life-changing consequences that are in there. So within our model, within TensorFlow, TensorFlow usually, this graph is pretty much taken from the Stanford machine learning white paper. But in TensorFlow, when you use when you plot your model, it will usually plot out an error model. And it will show you basically between validation and training data. And again, so what you're trying to do is check the accuracy and loss to evaluate the number of epochs in your model that's needed. In other words, when you have layers, you have those nodes, you want to have the right number of nodes, just enough to give you an accurate model. Sometimes people, they run 3 or 4 layers, they run maybe even more layers than that, and they find that maybe fewer nodes can give them a better accurate model than what they have. So this sort of graphic is what you're looking at when you run it within TensorFlow. And you can kind of see here, this kind of gives some idea. The underfit is basically saying that the training data is not really, it's probably too close to the validation in terms of no matter how many epochs you're adding or subtracting. So maybe questioning whether or not you're getting a real great model. The overfit is showing that as errors are decreasing, and you're increasing the number of epochs, yeah, you gain this wide gap between your validation and your training, basically. So that's something you should expect to see. But then, so the just right would be just in between, basically. Let's see how we're doing at time. 2:39. I think we got what we got. Okay, so let's see. I don't think this did not. Okay, so what we're going to do is this didn't give me the movie in here, but we're going to try to run this at the end. So let me get through. What I just explained is pretty much what a model should be for TensorFlow. There's a couple of adjustments that you would make. Just real quick for those who have asked, this is what RStudio looks like. It's pretty much 4 windows that you have here. But I have RStudio up, so we can probably run a model here. Now, after you run a model, you have a couple of functions that are available within TensorFlow to help you refine the model a little bit further. I mentioned about what's called a callback. Callback is a set of functions applied at different stages of the training procedure to view internal states of the model. So what this means is that and there's a ton of there's a lot of callback functions on TensorFlow's site. There's different types of there's at least 30 or so different callback functions, and you can actually create one depending on the type of model that you have too. But the idea with this is that you may have some activity that you may want to see while the model is going through certain. You want to view certain internal states. So let's say that for a forward, for example, you may have cost data associated with each decision that the customer makes. So you may want to have a callback that may help you figure out if that cost is hitting a certain target or breakpoint that your finance manager says, hey, we can't exceed this in order to keep our vehicle profitable. That's a great example. So when you think about models, thinking about what are the limits or considerations that you may want to have for your model. Another one, a similar type of one, is called early stopping. Now, it's similar to a callback, but the major difference is that it stops the training overall when the cost of validation is high. And what that means is that going back to the examples I had with the loss function, there's a cost for adding more nodes in terms of processing, in terms of that's what they mean in programming language. So the idea with this is that you might want to have an early stopping function that may help you to figure out where within the model that you may want it to stop when the cost validation is really high. There's not any further benefit, basically. And then there's also what's called a dropout. Now, dropout is a little bit more refined. Dropout drops out the epochs. They get filtered out of the training when certain features in your model are optimized prior to the training is completed. In other words, you might optimize a epoch, but the other epochs are still going through some sort of optimization. So what you can do is develop a dropout or set a dropout for that purpose. Now, you can inspect your runs. Actually, this might be helpful to us in this case. Let me make sure I'm watching the time. So the idea is that this training run. This is a function, and there's an actual package for this again called TFunds. TFunds, and what it does is that you can run it lets you see and compare your different training runs. So you have a training. It allows you to use a training run function. Lets you see the latest run, and there's also a compares run and what's called a list run, ls runs function that you can put into your script. What you see on the right is that when you add that function in, this pops up onto your RStudio screen, and the graph that you're seeing here is actually this is what I wanted to show running initially is the loss function at the top and then the accuracy. And the idea is that it shows the validation data and the test data, and where they cross is about the x-axis, by the way, is the number of epochs. So where they cross is showing you, giving you kind of an estimate of how many epochs are needed in the model to make it accurate, basically. So you can use this to get an idea, to have an idea of how many epochs you need in your model as you do your runs, give you to let you make a judgment call on that. So this is what, when you run TensorFlow, this graph is what you would, the graph you see is typically what you see, but TFunds kind of makes it convenient. Think of it as another version of Markdown. Just in this case, it's a Markdown for comparing your runs. Here, 245. Okay, so I got a couple more slides here, so I'll try to get through these pretty quickly. So TensorFlow Hub, this is an option that's available also within TensorFlow. And you use this for using what's called machine learning modules. And these are a smaller set of functions with a smaller data set that helps you to speed up training processes, improves generalization. That's a term that basically talks about, how the models off of the data, and how well it models is how you get into the loss and accuracy functions. But there's different there's different modules are out there, and TensorFlow has an entire hub, and that's available on the slides at the end here. But you can select based off of you can select the set that's been developed. Some of these are developed by Google, some of these are developed by other companies, and you can also create and submit these. So these are very similar. These are akin to templates you might see for Google Tag Manager, for example. But the idea of this is that it gives you a set of some additional functions and modules that you can play around with for your model as well. And they're loaded into your script. You can load it in via URL and then call it and then load it in as an object within your R function. I mean, within R script, and then call it like a function, basically. So it just makes it a little bit convenient. Now, one last bit too. For very large data sets, sometimes you might want to do something outside on the cloud rather than on your laptop. And this is where the library TF Deploy comes into play. TF Deploy is used to let you export and use what's called a TPU, which stands for TensorFlow Processing Unit, kind of like a GPU, basically, but designed for TensorFlow, or another cloud service for your very large data sets. And then it lets you run and use what's called a tensor board. Now, the tensor board is very similar to the tensor runs that you saw previously. It's just that this is, again, designed for running TensorFlow on the cloud. So again, you would use the library, you call that in your script, and you can again use that to connect to anything ranging from a TensorFlow server, cloud ML. I believe Azure. I'm not 100% sure. If not, there is. I would say if you don't see your preferred cloud service on here, there's probably a library that will let you connect to that service as well. So there's a number of options that you can build into this, basically. So let's get through the takeaways here. So couple of quick takeaways. So with TensorFlow, it's a machine learning framework. And what you want to do is you want to start with your data. You want to plan your variables so that way you don't have any sort of text in the observations. You want to have them in columns. And you want to plan for training and test data. An 80-20 split is great. Then you want to transform that layer, and then transfer your data, and then select and then form your layers. And then what you want to do ultimately is to train and inspect your data, so that way you're trying to figure out what the loss function is. And by doing that you get an idea of how to experiment to determine the right number of epochs that ensures that your model accuracy is great. So with that, I am going to see, are there any questions? Now, what I'm going to do is I'm going to go ahead and run a model. Let me see here. Let's try this. If not, I may have to record a video for the event here. So let's try something here real quick. Hang on. Bear with me. Okay. This didn't seem to work through. What I will do is I will go ahead and have the file put together. I have an MP4 that will run and show this as well. And that's also built into the Keynote slide as well. But real quick, before I let you go, just letting you know at the, let's see here, go back to the tab here real quick. At the end of the slide, what I've put on here, a couple of resources that will be helpful. TensorFlow.org has tutorials that can help you. And then I put on here the TensorFlow RStudio.com. This is where you get TensorFlow with R. There's a couple of tools on there that will help as well too. And they also have the tutorials on I mentioned about callback and the early stopping. There's a couple of tutorials and examples that we have built in there. So that's actually a starting point for using TensorFlow with R. And then also there are cheat sheets available. And then I would say the other thing is I'm also including the Stanford University sheet in here because it's really good, CS2229, very good on machine learning if you have not done machine learning before, kind of gives you a law of the lay of the land. And then there are two resources that are currently available. There's a TensorFlow user group, TFunds, which I think is a cool name. This is user groups that can help you in terms of how do you use TensorFlow. And there is, of course, the ever popular Stack Overflow forum, which can help you for asking and answering questions. So with that, I am going to go ahead and end right here. If there's no other question, I'll give a couple minutes. Are there any other questions? Okay. And I'm going to say thank you, first of all, for sitting into my presentation. I really appreciate it. And I look forward to talking with you again very, very soon.